Hello there. I'm so glad you found your way here tonight. Look up on any clear night and you will see them, tiny points of light scattered across the darkness. They seem still and silent, but they are anything but. Each one is a furnace of unimaginable power, burning for billions of years, forging the very atoms that make up your body. Some are so large they could swallow our entire solar system. Others are so dense that a teaspoon of their matter would weigh more than a mountain. And every single one is telling a story written in light across the vastness of space. Tonight, we journey into the hearts of the stars, the great engines of the universe. We will explore over 100 soothing facts about stars, about how they are born, how they live, and how they die, about the strange and wonderful objects they leave behind, about the light that has traveled for millions of years just to reach your eyes tonight. There is no test at the end, no pressure to remember anything, just the gentle pleasure of understanding the lights that have watched over humanity since the very beginning. So let your breathing slow. Let your body sink into wherever you are resting. And let these facts drift over you like starlight falling gently through a clear night sky. The stars are waiting, and tonight we explore them together. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the distant suns that fill our universe. Either way, this space is for you. There is something deeply peaceful about contemplating the stars. Every point of light in the night sky is a sun, often with its own planets, its own story, its own journey through the cosmos. Some have been burning since before Earth even existed. Others will continue to shine long after our world has passed. You are part of this story. The atoms in your body were forged in the hearts of stars that lived and died billions of years ago. The iron in your blood, the oxygen in your lungs, the calcium in your bones, all of it was once stardust scattered across the galaxy. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow. And let the weight of the day drift away like light, fading into the cosmic dark. Stars are patient beyond measure. They burn for billions of years without hurrying. They forge elements atom by atom without rushing. They live and die on timescales that dwarf everything we know. And yet, within all that slowness, there are sudden bursts of wonder. Supernovae that outshine entire galaxies. Neutron stars that spin hundreds of times per second. Black holes that swallow light itself. Tonight, we will wander through this magnificent cosmos. We will meet stars so massive they defy imagination, and stars so small they could burn for trillions of years. We will discover processes that create the very elements of life, and witness the strange afterlives of stars that have died. But there is no hurry. The stars have been shining for billions of years. They can wait a little longer while you rest. Let us begin with the giants of the universe. The largest known stars could swallow Earth's orbit whole. The most massive stars in the universe defy the limits of imagination. If placed at the center of our solar system, some of these stellar giants would extend far beyond the orbit of Earth, engulfing Mercury, Venus, and our own planet entirely. Stars like UY Scuti and Stephenson 2-18 are so enormous that their surfaces would stretch past Mars and even approach the orbit of Jupiter. These hypergiant stars are hundreds of times more massive than our Sun and vastly less dense, their outer layers spread thin across immense volumes. Despite their incredible size, these giants are relatively short-lived, burning through their fuel far faster than smaller stars. Their lifetimes are measured in mere millions of years, rather than the billions our Sun enjoys. Standing on Earth, it is humbling to realize that such colossal objects exist in the same universe where we live our brief lives. Some stars burn hot enough to outshine entire galaxies. The most luminous stars pour out energy at rates that seem almost impossible. A single hypergiant star can radiate as much light as billions of ordinary suns combined. These incredibly luminous objects belong to a rare class of stellar monsters that burn through their nuclear fuel at ferocious rates. Stars like Eta Carinae and the Pistol star emit more energy in a few seconds than our Sun produces in years. This extreme brightness makes them visible across vast cosmic distances, shining like beacons through the darkness of space. However, their brilliance comes at a cost. These stars consume their fuel rapidly and live short, violent lives. In cosmic terms, they burn bright and fast before meeting explosive ends. Their light reaches us as evidence of the extremes that stellar physics can achieve. Hypergiants can lose more mass than the Sun every year. Some of the largest stars in the universe are not only immense, but also wildly unstable. Hypergiants shed material at astonishing rates through powerful stellar winds, sometimes ejecting as much mass as an entire Sun over just a few years. This mass loss can be so dramatic that the star is surrounded by vast shells and nebulae of expelled gas. The expelled material enriches the surrounding space with heavy elements forged in the star's core. Stars like VY Canis Majoris are famous for their turbulent eruptive behavior, shedding layers of their outer atmospheres in violent outbursts. This shedding gradually strips the star down, changing its structure and fate. The mass a hypergiant loses in its lifetime can profoundly affect how it eventually dies. Red supergiants are among the coolest, yet largest stars. Despite their tremendous size, red supergiants are relatively cool by stellar standards. Their surface temperatures are much lower than those of smaller, hotter stars like our Sun, giving them their distinctive red color. This coolness allows their outer layers to expand enormously, creating bloated giants that dwarf smaller, hotter suns. Betelgeuse, one of the most famous red supergiants, is visible to the naked eye as the red shoulder of the constellation Orion. Inside these colossal stars, nuclear fusion continues in layered shells, producing heavier and heavier elements as the star ages. Red supergiants represent a late stage in stellar evolution, a prelude to the dramatic death that awaits them. Their cool, glowing surfaces are among the most beautiful sights in the night sky. Some stars spin so quickly they flatten into oblate shapes. Rotation has a profound effect on the shape of a star. When a star spins rapidly, centrifugal forces push material outward along its equator, causing it to bulge. The result is a star that is no longer perfectly spherical, but flattened at the poles, and wider at the middle, an oblate shape. Some of the fastest spinning stars bulge so dramatically that their equatorial diameters are noticeably larger than their polar ones. This flattening affects the star's temperature distribution and the way it radiates light. Extremely rapid rotation can even cause material to be flung off the star entirely. The fastest spinning stars push the limits of how quickly a stable stellar object can rotate without tearing itself apart. Rotation remains one of the key factors shaping the lives and appearances of stars. Wolf-Rayet stars shed matter in powerful stellar winds. Wolf-Rayet stars are some of the most violent and energetic objects in the stellar zoo. They are evolved, massive stars that have blown away their outer hydrogen layers, exposing the hot, dense cores beneath. These exposed cores radiate intensely and drive ferocious stellar winds that sweep material outward at thousands of kilometers per second. The winds carry away vast quantities of mass, enriching the surrounding space with heavy elements like carbon, nitrogen, and oxygen. Wolf-Rayet stars are surrounded by glowing bubbles of expelled gas, sculpted by their relentless outflows. These stars represent a final, unstable stage before a massive star explodes as a supernova. Their luminosity and mass loss make them among the most extreme stellar objects known. The smallest stars can burn for trillions of years. The tiniest stars in the universe, the red dwarfs, have lifetimes almost beyond comprehension. Because they burn their nuclear fuel so slowly and efficiently, they can continue shining for trillions of years. This is far longer than the current age of the universe, which is only about 14 billion years old. No red dwarf that has ever formed has yet had time to die a natural death. These patient, dim stars will still be glowing when most of the brighter, more massive stars have long since exploded and faded. Red dwarfs are incredibly common, making up the vast majority of all stars in the Milky Way. Their patience and efficiency make them potential homes for life across cosmic timescales. In a universe destined for darkness, red dwarfs will be among the last lights to go out. The slow burning of these stars represents a strategy for survival that far outlasts the flashier approach of massive stars. Red dwarfs are the most common stars in the universe. Though they are small and dim, red dwarfs vastly outnumber all other types of stars. Estimates suggest that around 3/4 of all stars in the Milky Way are red dwarfs. They are so faint, however, that none are visible to the naked eye from Earth. Only with telescopes can astronomers detect these dim, numerous suns scattered throughout the galaxy. Their sheer abundance means that they represent the typical star in the universe, while our bright yellow sun is actually relatively rare. Many red dwarfs host planets, including some in the habitable zone where liquid water might exist. Because of their long lifetimes and great numbers, red dwarfs may be the most likely hosts for life in the cosmos. These humble stars redefine what it means to be ordinary in the stellar world. The ubiquity of red dwarfs makes them one of the most important classes of stars for the search for extraterrestrial life. Yellow stars like the Sun are actually quite ordinary. Our Sun is a G-type main sequence star, a category that includes many other stars scattered throughout the galaxy. These yellow stars are middle of the road in almost every respect. Not too hot, not too cool, not too massive, not too small. Their balanced properties make them neither the most common nor the most rare type of star. Yellow stars burn for several billion years, long enough for planets around them to develop and sustain complex life. The Sun sits roughly in the middle of its lifespan, with about 5 billion years of steady burning still ahead. Despite its familiarity, our Sun represents a special niche in the cosmic zoo, stable, long-lived, and hospitable. The ordinariness of yellow stars is part of what makes them so favorable for the development of life. Yellow stars provide just the right combination of warmth, stability, and longevity to nurture worlds like our own. Brown dwarfs blur the line between planets and stars. Brown dwarfs occupy a strange middle ground between stars and giant planets. They form in the same way as stars, from contracting clouds of gas and dust, but they lack the mass to sustain hydrogen fusion in their cores. As a result, they glow dimly from residual heat and slowly cool over time. The boundary between a brown dwarf and a large planet like Jupiter is not sharply defined, leading to fascinating debates among astronomers. Brown dwarfs can be difficult to detect because of their faintness, but surveys have identified many in the Sun's neighborhood. These objects are not quite stars and not quite planets, representing a category all their own. Brown dwarfs remind us that the universe is full of intermediate objects that defy simple classification. The discovery of brown dwarfs has expanded our understanding of how objects form from collapsing clouds of gas. Low-mass stars burn fuel slowly and efficiently. The smallest hydrogen-fusing stars, the red dwarfs, are remarkably efficient burners. Because their cores are cooler and reactions proceed more slowly, they consume their fuel at a tiny fraction of the rate of larger stars. This efficiency translates into staggeringly long lifetimes, measured in tens of billions to trillions of years. Low-mass stars also convect material throughout their interiors, mixing fresh fuel into the core and extending their lives even further. The gentle pace of fusion in these stars means they radiate relatively little light at any given moment. Despite their faintness, their longevity ensures that they will contribute to the light of galaxies for eons to come. Efficiency, in the stellar world, often means endurance. The patient burning of low-mass stars contrasts sharply with the profligate energy output of their more massive siblings. Over trillions of years, only faint red stars will remain. As the universe ages, the brightest and most massive stars will exhaust their fuel and die off. One by one, the giants, supergiants, and even ordinary sun-like stars will fade into white dwarfs, neutron stars, or black holes. In the far distant future, only the slowest burning red dwarfs will still shine. These dim embers will be the last natural sources of light in a darkening cosmos. Their reign will last for trillions of years, far longer than the current age of the universe. Eventually, even the red dwarfs will run out of fuel and cool into darkness. The universe's final stellar era will belong to the humblest stars of all. The longevity of red dwarfs ensures they will be the final witnesses to the end of the stellar age. Stars are born in giant molecular clouds of gas and dust. The birthplaces of stars are vast clouds of cold gas and dust that drift through galaxies. These molecular clouds can span hundreds of light years and contain enough material to form thousands or even millions of stars. Within these clouds, gravity slowly draws matter together into denser regions called cores. As a core contracts, it heats up from the pressure of its own weight. Over millions of years, the collapsing material forms a protostar at its center. The surrounding cloud continues to feed the growing protostar with fresh gas and dust. Star formation is a slow and patient process, hidden from view behind thick veils of obscuring dust. The largest molecular clouds in our galaxy are so massive that they can birth entire clusters of stars in a single episode of formation. Protostars glow before nuclear fusion even begins. Even before a young star ignites nuclear fusion in its core, it already glows with significant brightness. This glow comes not from fusion but from the heat generated by gravitational contraction. As material falls inward and the protostar compresses, the released gravitational energy is converted into thermal radiation. Protostars can shine for hundreds of thousands of years before fusion finally ignites. During this phase, the young star is swaddled in a cocoon of gas and dust that absorbs most of its visible light. Infrared telescopes can peer through this shroud and reveal protostars hidden within molecular clouds. The warmth of gravity's embrace lights these stellar infants before their nuclear fires begin. This pre-fusion glow can be nearly as bright as the mature star will eventually become. The youngest stars are often hidden behind dust. The dusty environments in which stars are born obscure the earliest stages of their lives from view. Visible light from newborn stars is absorbed by the surrounding gas and dust, making them invisible to optical telescopes. Only by observing in infrared or radio wavelengths can astronomers reveal these hidden stellar nurseries. Once a young star becomes powerful enough, its radiation and stellar winds begin to clear away the natal material. Eventually, the star emerges from its dusty womb and becomes visible at optical wavelengths. The transition from hidden to revealed marks a major phase in a young star's development. The dust that hides them also provides the raw material from which planets will later form. Some of the youngest stars remain hidden for millions of years before they finally break free of their cocoons. Young stars often blast jets into space. Many newborn stars drive powerful bipolar jets of material that shoot out along their rotational axes. These jets can extend for light years, punching through the surrounding clouds and leaving glowing trails in their wake. The jets are thought to carry away excess angular momentum, allowing the forming star to continue accreting material without spinning out of control. Herbig-Haro objects, the glowing patches where jets collide with surrounding gas, are some of the most striking features of stellar nurseries. Jets can be observed at multiple wavelengths and provide valuable information about the processes occurring close to the protostar. As the star matures and clears its surroundings, the jets eventually weaken and disappear. These cosmic fountains are signatures of the violent birth of new suns. The energy carried by these jets can have a significant impact on the surrounding molecular cloud. Stellar nurseries can stretch across hundreds of light years. The regions where stars form are among the largest structures in galaxies. Giant molecular clouds can span hundreds of light years and contain millions of solar masses of gas and dust. Within these vast complexes, multiple generations of stars may form over millions of years. Famous examples include the Orion Molecular Cloud and the Carina Nebula, which are visible from Earth and actively producing new stars. The internal structure of these clouds is complex, with dense cores, filaments, and sheets of gas interacting through gravity and radiation. Massive stars formed within these nurseries can influence subsequent generations by compressing nearby gas with their winds and supernova explosions. Stellar nurseries are the factories that continuously replenish galaxies with fresh suns. These immense regions contain enough raw material to birth stars for millions of years to come. Stars can form disks that give birth to planets. As a protostar forms, the material around it naturally flattens into a rotating disk due to conservation of angular momentum. These protoplanetary disks are the birthplaces of planets, moons, asteroids, and comets. Within the disk, dust grains collide and stick together, gradually building up larger and larger bodies. Over millions of years, these bodies can grow into rocky planets or gas giants, depending on their location and available material. Many young stars are surrounded by visible disks that have been directly imaged by telescopes. The structure and composition of these disks determine the architecture of the planetary systems that will eventually emerge. Every planet, including Earth, traces its origins to such a dusty disk around a newborn star. The diversity of planetary systems discovered around other stars reflects the variety of conditions found in these formative disks. Stars are nuclear fusion reactors in space. At the heart of every star lies a nuclear furnace, where atoms are fused together under extreme temperatures and pressures. This process of nuclear fusion releases enormous amounts of energy in the form of light and heat. The conditions required for fusion are extraordinary, temperatures of millions of degrees and pressures millions of times greater than Earth's atmosphere. In the Sun's core, hydrogen nuclei are smashed together with such force that they overcome their natural repulsion and merge. The energy released by these reactions powers the star and prevents it from collapsing under its own gravity. Every second, the Sun converts millions of tons of hydrogen into helium, releasing energy that eventually reaches Earth as sunlight. Stars are the universe's primary energy sources, running on the same physics that powers hydrogen bombs. The photons generated in the core take hundreds of thousands of years to reach the surface, bouncing through the dense interior before finally escaping into space. Fusion in stars transforms hydrogen into helium. The dominant fusion process in most stars is the conversion of hydrogen into helium. Through a series of reactions known as the proton-proton chain, 4 hydrogen nuclei are fused to create one helium nucleus. A small fraction of the original mass is converted directly into energy, according to Einstein's famous equation. This mass-to-energy conversion is the source of the vast power output of stars. In more massive stars, a different set of reactions called the CNO cycle also contributes to hydrogen burning. The helium produced accumulates in the core, gradually changing the star's internal structure over time. This simple transformation of hydrogen into helium is the fundamental reaction that keeps stars shining. The entire main sequence lifetime of a star is dominated by this single, elegant process of converting hydrogen into helium. Stars balance gravity with outward pressure from fusion. A star exists in a state of dynamic equilibrium between two opposing forces. Gravity pulls the star's mass inward, attempting to compress it into the smallest possible volume. At the same time, the energy released by fusion creates an outward pressure that resists this compression. As long as fusion continues at a rate that balances gravity, the star remains stable. This equilibrium can last for millions or billions of years, depending on the star's mass. Any disturbance to this balance triggers adjustments. If fusion decreases, the core contracts and heats up, accelerating reactions until equilibrium is restored. Stars are self-regulating systems, constantly adjusting to maintain their delicate balance. The tug-of-war between gravity and pressure is the essence of stellar life. This self-regulation is what allows stars to burn steadily for such incredibly long periods of time. Without fusion, stars would collapse instantly. If a star's fusion reactions were suddenly to cease, there would be nothing to counteract the inward pull of gravity. The star would begin to collapse almost immediately under its own weight. This collapse would proceed rapidly, on timescales of minutes to hours depending on the star's mass. In reality, the core of a massive star does experience just this scenario when it runs out of nuclear fuel. The sudden collapse leads to catastrophic events such as supernova explosions or the formation of neutron stars and black holes. For low-mass stars, the collapse is more gradual, eventually producing a white dwarf. The ongoing presence of fusion is what keeps stars from succumbing to their own gravity. Without it, the universe would be filled with dark, collapsed remnants. Fusion is the engine that holds the star together against the relentless inward pressure of gravity. Iron marks the point where fusion can no longer power a star. Elements heavier than hydrogen and helium are forged in the cores of massive stars through successive stages of fusion. Each stage produces heavier elements, from helium to carbon, oxygen, silicon, and beyond. However, this process has a limit: iron. Fusing iron nuclei does not release energy. Instead, it absorbs energy. When a star's core fills with iron, there is no longer any source of outward pressure to counteract gravity. At this moment, the core collapses catastrophically, triggering a supernova explosion. The iron core represents the end of the line for nuclear fusion as an energy source. Everything the star has built over millions of years comes crashing down in seconds. Iron is both the triumph and the doom of massive stars. The accumulation of iron in the core is the death sentence that seals the fate of every massive star. Some stars burn fuel 1,000,000 times faster than the Sun. The most massive stars are not just bigger versions of the Sun, they are fundamentally different in their behavior. Their cores are hotter and denser, driving fusion reactions at rates vastly higher than those in smaller stars. A star with 50 times the Sun's mass might consume its hydrogen 1,000,000 times faster, drastically shortening its lifespan. While the Sun will burn for about 10 billion years, a massive star might exhaust its fuel in just a few million. This rapid burning also produces a much greater luminosity, making massive stars among the brightest objects in the galaxy. Their prodigious energy output shapes the environments around them and seeds the cosmos with heavy elements. Speed, in stellar terms, is a double-edged sword. The reckless burning of massive stars ensures they live fast and die young compared to their smaller cousins. A star's color reveals its temperature. The color of a star is not merely decorative, it is a direct indicator of its surface temperature. Hot stars glow blue or white, while cooler stars radiate in shades of yellow, orange, or red. This relationship between color and temperature follows the laws of blackbody radiation. The hottest stars can have surface temperatures exceeding 30,000 degrees, giving them their intense blue hue. Cooler red giants might have temperatures of only 3,000 degrees, far lower than the Sun's roughly 6,000. By studying the color of starlight, astronomers can determine temperatures across vast cosmic distances. Color is one of the most basic and powerful tools in stellar astrophysics. Even a quick glance at the night sky reveals the range of stellar temperatures through the variety of colors visible. White stars burn hotter than blue flames. In everyday experience, we associate blue with coolness and red with heat, but the physics of stars reverses this intuition. The hottest stars appear blue or blue-white, while the coolest ones glow red. White stars occupy a middle ground, cooler than blue giants, but still intensely hot by any earthly standard. A white star like Sirius has a surface temperature of about 10,000 degrees, nearly twice that of the Sun. This counterintuitive relationship is explained by the way hotter objects emit shorter wavelengths of light. Blue light has a shorter wavelength than red, so hotter objects peak in the blue part of the spectrum. The color of a star is a window into its energy. Understanding this relationship was one of the key breakthroughs in the development of astrophysics. Stars come in colors the human eye can barely see. The light emitted by stars spans far more than the visible spectrum. The hottest stars radiate much of their energy as ultraviolet light, invisible to human eyes. Cooler stars emit substantial amounts of infrared radiation, which we perceive only as heat. Telescopes equipped with sensors for these wavelengths reveal a universe of color that the unaided eye can never see. Even within the visible range, the apparent colors of stars can be subtle. and require careful observation. Light pollution and atmospheric effects can wash out the delicate hues of distant suns. The true palette of the stellar sky is richer than it first appears. To fully appreciate the colors of stars, one must escape the glow of cities and observe under dark, clear skies. The rarest stars are the most massive blue giants. Blue giants and supergiants are among the rarest objects in the galaxy. Their extreme brightness makes them visible across vast distances, but they are vastly outnumbered by smaller, cooler stars. The formation of such massive stars requires exceptional conditions in stellar nurseries. Once formed, they burn through their fuel rapidly, living only a few million years before exploding as supernovae. Their rarity is compounded by their short lifetimes. At any given moment, few blue giants exist compared to the countless red dwarfs. Despite their scarcity, blue giants have an outsized influence on their surroundings, ionizing gas and triggering the formation of new stars. Their rarity makes each one a cosmic treasure. The intense radiation from blue giants shapes the interstellar medium for light years in every direction. Some stars pulse in brightness with cosmic heartbeats. Variable stars change in brightness over time, sometimes with remarkable regularity. Pulsating variables, like Cepheids and RR Lyrae stars, expand and contract in rhythmic cycles lasting days to weeks. This pulsation causes their luminosity to rise and fall in a predictable pattern. The physics of pulsation involves a delicate interplay between pressure, temperature, and opacity in the star's outer layers. Cepheid variables have become essential tools for measuring cosmic distances, because their pulsation periods correlate with their intrinsic brightness. By observing how bright a Cepheid appears and how long its cycle lasts, astronomers can determine how far away it is. These stellar heartbeats have extended our reach into the depths of the universe. The discovery of the period luminosity relationship for Cepheids was one of the key breakthroughs in measuring the scale of the cosmos. Many of the stars you see are actually multiple systems. What appears to the naked eye as a single point of light is often a complex system of 2, 3, or more stars orbiting together. Binary and multiple star systems are remarkably common. Some estimates suggest that more than half of all Sun-like stars have at least one companion. These companions can range from close pairs that nearly touch to distant partners separated by hundreds of astronomical units. The dynamics of multiple star systems create a rich variety of orbital configurations and evolutionary pathways. Some systems are so tight that the stars exchange material, profoundly affecting their evolution. Others are so widely spaced that their mutual gravity barely influences their individual fates. The night sky is populated by families of stars, rather than solitary suns. Our own sun may be somewhat unusual in having no stellar companion, making our solar system somewhat rare in the cosmic census. Binary stars can steal mass from one another. In close binary systems, stars can gravitationally capture material from their partners. This mass transfer occurs when one star expands, often as it evolves off the main sequence, and spills matter onto its companion. The transferred material can form a swirling accretion disk around the receiving star. Mass transfer can dramatically alter the masses, evolution, and ultimate fates of both stars in the system. In some cases, the mass-receiving star can be pushed past critical limits, triggering nova eruptions, or even supernovae. The interplay between binary companions creates some of the most violent and exotic phenomena in the stellar universe. Stars that live together, can profoundly reshape each other's destinies. The exchange of mass between binary stars creates stellar evolution pathways that would be impossible for isolated stars. Triple star systems can create strange orbital paths. When three or more stars share a gravitational bond, the resulting orbits can become extraordinarily complex. The gravitational interactions between three bodies do not yield simple, stable solutions like those of two-body systems. As a result, triple systems can exhibit chaotic behaviors, with orbits evolving unpredictably over long timescales. Some configurations settle into hierarchical arrangements, with a close pair orbited by a distant third star. Others remain dynamically unstable, eventually ejecting one member entirely. Triple and higher-order systems challenge our understanding of gravitational dynamics. The dance of three stars is far more intricate than that of two. The study of these complex systems has deep connections to chaos theory and the fundamental limits of predictability in physics. Planets can orbit multiple stars at once. Circumbinary planets are worlds that orbit around two stars rather than one. These exotic planets experience skies with two suns, sometimes rising and setting together, other times at odd intervals. The gravitational environment of a binary star can create stable zones where planets form and persist. Several circumbinary planets have been discovered by space telescopes, confirming that such systems are not merely theoretical curiosities. The presence of two stars can affect the climate and lighting conditions on circumbinary worlds in complex ways. For life to develop on such a planet, it would have to adapt to entirely different rhythms of day and night. The universe offers planetary settings far stranger than anything in our own solar system. These discoveries have expanded our imagination of what alien worlds might be like. Stars can merge to form even larger suns. Under certain conditions, two stars in a binary system can spiral together and eventually merge into a single, more massive star. This process can be triggered by orbital decay, mass transfer, or gravitational interactions with a third body. Stellar mergers release enormous amounts of energy and can produce transient events visible across the galaxy. The resulting star may have unusual properties, such as rapid rotation or an unusual chemical composition. Mergers are thought to create some of the blue straggler stars observed in globular clusters, which appear younger than their neighbors. The collision of stars is a reminder of how dynamic and violent the universe can be. Even suns are not immune to cosmic collisions. These merger events can briefly rival supernovae in brightness, as the two stars become one. Colliding stars can produce gravitational waves. When two compact stellar remnants such as neutron stars or black holes spiral together and merge, they produce ripples in the fabric of space-time known as gravitational waves. These waves were first directly detected in 2015 and have since opened a new window on the universe. The inspiral and merger of stellar remnants releases tremendous energy, detectable by instruments on Earth. Gravitational wave observations have confirmed predictions of general relativity and revealed new classes of stellar events. The collision of two neutron stars in 2017 was observed both in gravitational waves and across the electromagnetic spectrum. Such multi-messenger astronomy is transforming our understanding of the cosmos. The final moments of merging stars now echo through the universe as waves of gravity. This new way of observing the universe has been called the beginning of gravitational wave astronomy. Star clusters can host hundreds of thousands of suns. Star clusters are gravitationally bound collections of stars that formed from the same molecular cloud. The largest of these, globular clusters, can contain hundreds of thousands of stars packed into a relatively small volume of space. Within these dense stellar swarms, the average distance between neighboring stars is much smaller than in the Sun's neighborhood. The gravitational interactions in such crowded environments shape the evolution of stars and can lead to unusual stellar types. Globular clusters are among the oldest structures in galaxies, with some having formed more than 12 billion years ago. Their stars orbit a common center of mass, creating a spherical or slightly elliptical distribution. These ancient cities of stars are windows into the early history of the cosmos. If you could travel to the center of a globular cluster, the night sky would be ablaze with thousands of brilliant suns. Globular clusters contain some of the oldest stars in the universe. The stars within globular clusters formed when the universe was young, often within the first few billion years after the Big Bang. Because of their great age, these stars have low abundances of elements heavier than helium, reflecting the chemistry of the early cosmos. Studying globular cluster stars allows astronomers to understand the conditions of the ancient universe. Their ages provide lower limits on the age of the universe itself. Globular clusters orbit galaxies in halos that extend far beyond the visible disk of stars. They are relics of a time when galaxies were still forming and merging. The oldest stars in these clusters have been shining since before Earth or the Sun existed. These stellar elders have witnessed the entire history of galactic evolution, from their lonely outposts in the halo. Some clusters are billions of years old. Both globular and open clusters can persist for vast spans of time, though their lifetimes differ. Globular clusters are so tightly bound that they can survive for the entire age of the universe. Open clusters, which are more loosely structured, gradually disperse as gravitational encounters scatter their members into the surrounding galaxy. Some open clusters persist for hundreds of millions of years before dissolving. The age of a cluster can be determined by studying the distribution of stars on the Hertzsprung-Russell diagram. The oldest clusters contain only red and orange stars, while younger clusters still have hot blue members. Cluster ages are cosmic clocks, marking the passage of billions of years. By studying clusters of different ages, astronomers can trace the history of star formation in the galaxy. Open clusters slowly dissolve into the galaxy. Unlike their globular cousins, open clusters are loosely bound and vulnerable to disruption. Over time, gravitational encounters with giant molecular clouds, spiral arms, and other structures strip away member stars. This gradual erosion eventually dissolves the cluster entirely, spreading its former members throughout the galactic disk. The Sun itself may once have belonged to an open cluster that has long since dispersed. Young open clusters like the Pleiades still show hundreds of stars clumped together, but older clusters are sparse and faint. The members of a dissolving cluster continue to travel through space together for a time, forming a moving group. Open clusters represent transient assemblies of stars destined for eventual separation. The stars of a dissolved cluster carry the same chemical fingerprint, marking them as siblings even after they have gone their separate ways. Some ancient stars in the Milky Way are nearly as old as the universe. The oldest stars in our galaxy are found in the halo and in globular clusters, far from the star-rich disk. These ancient suns formed within the first billion years after the Big Bang, making them nearly as old as the universe itself. They are characterized by very low abundances of heavy elements, since those elements had not yet been synthesized by earlier generations of stars. Studying these primordial stars reveals the chemical and physical conditions of the early universe. Some of the oldest known stars are found in our galactic backyard, close enough for detailed spectroscopic analysis. Their existence confirms that the Milky Way has a history stretching back to the cosmic dawn. These venerable suns are living fossils of the early universe. Each ancient star is a time capsule, preserving information about the conditions that prevailed when the universe was young. Some stars die quietly, others in explosive cataclysms. The fate of a star depends almost entirely on its mass. Low-mass stars like the Sun will end their lives gently, shedding their outer layers and fading into white dwarfs. Massive stars, by contrast, die violently in supernova explosions that scatter their remains across space. Between these extremes lies a spectrum of possible endings, each governed by the interplay of gravity, nuclear physics, and stellar structure. The quiet deaths of smaller stars can still be beautiful, producing glowing planetary nebulae. The violent deaths of giants seed the cosmos with the heavy elements necessary for planets and life. Stellar death is not merely an ending, but a transformation that fuels the next generation of cosmic creation. The way a star dies determines what kind of remnant it leaves behind, whether a white dwarf, neutron star, or black hole. The Sun will one day expand into a red giant. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core, triggering a dramatic transformation. The core will contract and heat up, while the outer layers expand to many times their current size. The Sun will swell into a red giant, engulfing the inner planets and perhaps reaching as far as Earth's orbit. Its surface will cool, even as its total luminosity increases. This phase will last for hundreds of millions of years before the outer layers are ejected and the core is exposed as a white dwarf. The Sun's transformation will reshape the solar system entirely. What was once the source of life will become a harbinger of destruction. Long before the Sun becomes a red giant, the increasing luminosity will have made Earth uninhabitable for life as we know it. Stars can leave behind planetary nebulae as cosmic grave markers. When a Sun-like star reaches the end of its life, it sheds its outer layers in a gentle outflow that creates a planetary nebula. The exposed core at the center ionizes the surrounding gas, causing it to glow in vivid colors. Planetary nebulae display a remarkable variety of shapes, from simple spheres to intricate bipolar structures. These glowing shells last only tens of thousands of years before dispersing into the interstellar medium. The name is a misnomer, dating from a time when astronomers mistook their round shapes for planets. Despite their fleeting existence, planetary nebulae enrich the galaxy with the products of stellar nucleosynthesis. They are among the most beautiful objects in the sky. Each planetary nebula is a monument to the star that created it, a brief but brilliant farewell to the cosmos. The death of a star can trigger the birth of new ones. When a massive star explodes as a supernova, it sends a shockwave racing through the surrounding interstellar medium. This shockwave can compress nearby molecular clouds, initiating the gravitational collapse that leads to star formation. In this way, the death of one star sows the seeds for the next generation. Supernova remnants often border or intersect with active star-forming regions. The heavy elements scattered by the explosion become incorporated into new stars and planets. This cycle of stellar birth and death has been repeating for billions of years, enriching the galaxy with each generation. Death and birth are intimately linked in the cosmic life cycle. The energy of a dying star becomes the trigger for the creation of new suns and new worlds. some stars explode more than once in rare supernova rebounds. In rare cases, a massive star's death is not a single event, but a series of explosions. Pulsational pair instability supernovae can eject material in successive outbursts before a final, terminal explosion. These episodic ejections create layered shells of debris around the star. When the final supernova occurs, the shockwave collides with this pre-ejected material, producing unusually bright and long-lasting transient events. Such explosions challenge our understanding of how the most massive stars end their lives. Observational evidence for these multi-stage deaths is still being accumulated. The deaths of the largest stars are even more complex than once believed. These repeated explosions make the final death throes of the most massive stars some of the most spectacular events in the cosmos. Supernovae scatter heavy elements across the galaxy. When a massive star explodes as a supernova, it ejects the elements forged in its core into interstellar space. These elements include oxygen, carbon, silicon, iron, and heavier nuclei synthesized in the final moments of the explosion. The debris from countless supernovae over billions of years has enriched the interstellar medium with the raw materials for planets and life. Without supernovae, the universe would contain only hydrogen, helium, and trace amounts of lithium. Every atom of iron in your blood and calcium in your bones was once scattered by an exploding star. Supernovae are the universe's great recyclers, transforming stellar remains into the building blocks of new worlds. These violent events are essential for cosmic chemical evolution. The expanding remnants of supernovae can be visible for tens of thousands of years as glowing shells of gas. Type Ia supernovae help us measure the size of the universe. Type Ia supernovae are a special class of stellar explosions that occur in binary systems containing a white dwarf. When the white dwarf accumulates enough mass from its companion, it reaches a critical point and detonates. Because the triggering mass is always roughly the same, these explosions have a remarkably consistent peak brightness. This makes them excellent standard candles for measuring cosmic distances. By comparing the observed brightness of a Type Ia supernova to its known intrinsic luminosity, astronomers can calculate how far away it is. Observations of distant Type Ia supernovae led to the discovery that the universe's expansion is accelerating. These stellar explosions have reshaped our understanding of cosmic history. The discovery of the accelerating universe using Type Ia supernovae was awarded the Nobel Prize in Physics in 2011. Massive stars end their lives in spectacular explosions. The most massive stars, those with more than about 8 times the Sun's mass, inevitably die in core collapse supernovae. When such a star exhausts its nuclear fuel, its core collapses under gravity in a fraction of a second. The infalling material bounces off the newly formed neutron core, creating an outward shockwave that tears the star apart. The resulting explosion can briefly outshine entire galaxies and is visible across millions of light-years. Core collapse supernovae leave behind either neutron stars or black holes, depending on the mass of the original star. These explosions release more energy in seconds than the Sun will produce over its entire lifetime. The deaths of giants are among the most energetic events in the universe. The sudden transition from a massive star to a compact remnant happens in a cosmic blink of an eye. The first stars may have been hundreds of times more massive. In the early universe, the first generation of stars formed from gas that contained no elements heavier than lithium. Without these cooling agents, the collapsing gas clouds remained hot and the resulting stars were much more massive than those forming today. Some theoretical models suggest these primordial stars could have been hundreds of times more massive than the Sun. Such stars would have burned fiercely for only a few million years before exploding as superluminous supernovae. Their deaths seeded the universe with the first heavy elements, paving the way for subsequent generations of stars and planets. No first-generation star survives today. They all died long ago. Their legacy lives on in the enriched material that forms modern stars. The first stars were cosmic pioneers, blazing brightly in a universe that had never seen starlight before. Supernovae can briefly outshine entire galaxies. At their peak, the brightest supernovae can emit as much light as billions of ordinary suns combined. For a few weeks, a single exploding star can rival or even exceed the total luminosity of the galaxy that hosts it. This extreme brightness makes supernovae visible across vast cosmic distances. Historical supernovae visible to the naked eye were recorded by astronomers in ancient China, the Middle East, and Europe. Modern surveys detect thousands of supernovae each year in distant galaxies. Their brightness curves and spectra provide valuable information about stellar physics and cosmic distances. A single stellar death can, for a brief moment, dominate the light of trillions of stars. These fleeting beacons have helped astronomers map the structure and expansion history of the universe. Neutron stars are the remains of stellar explosions. When a massive star explodes as a supernova, its core collapses into an extraordinarily dense remnant called a neutron star. In this collapse, protons and electrons are crushed together to form neutrons, creating matter unlike anything found on Earth. Neutron stars pack more mass than the Sun into a sphere only about 20 kilometers across. The density is so extreme that a sugar cube-sized sample would weigh as much as a mountain. Neutron stars are born spinning rapidly and gradually slow over millions of years. They represent one of the most exotic endpoints of stellar evolution. These compact objects are laboratories for physics under conditions impossible to recreate on Earth. The study of neutron stars has provided insights into fundamental physics that no other observations could offer. Their existence was predicted decades before they were first detected. A teaspoon of neutron star material would weigh billions of tons. The density of neutron star matter is almost beyond comprehension. A single teaspoon of material from a neutron star would weigh about 1 billion tons, roughly equivalent to the mass of a large mountain. This incredible density arises from the gravitational compression of matter into a degenerate state composed almost entirely of neutrons. The surface gravity of a neutron star is about 100 billion times that of Earth. If you could stand on a neutron star, you would be flattened into a layer less than an atom thick in an instant. The physics of neutron star interiors involves exotic states of matter not yet fully understood. These extreme objects push the limits of known physics. Scientists believe the cores of neutron stars may contain forms of matter that do not exist anywhere else in the universe. Neutron stars are truly the strangest macroscopic objects in nature. Pulsars spin hundreds of times per second. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the star spins, these beams sweep through space like the beams of a lighthouse. If Earth lies in the path of a beam, we detect regular pulses of radio waves, X-rays or gamma rays. Some pulsars spin as slowly as once every few seconds, while the fastest, called millisecond pulsars, rotate hundreds of times per second. Millisecond pulsars are thought to have been spun up by accreting matter from a companion star. The regularity of pulsar signals is so precise that they rival atomic clocks in accuracy. Pulsars have been used to test general relativity and search for gravitational waves. The first pulsar was discovered in 1967 and initially puzzled astronomers, who briefly considered the possibility that it might be a signal from an alien civilization. Today, thousands of pulsars have been catalogued throughout our galaxy. Magnetars have magnetic fields strong enough to rip atoms apart. Magnetars are a special class of neutron stars with magnetic fields trillions of times stronger than Earth's. These fields are so intense that they could erase the magnetic strip on a credit card from a distance of halfway across the galaxy. At close range, the magnetic field would distort the electron clouds of atoms, disrupting chemistry and biology. Magnetar eruptions release enormous bursts of energy, detectable across the Milky Way. The origin of these extreme magnetic fields is still debated, but they are thought to arise during the violent formation of the neutron star. Magnetars are among the most powerful magnets in the universe. Their fields create environments where matter and light behave in strange and exotic ways. A magnetar located within a few 100,000 kilometers of Earth would be lethal to all life on our planet. These rare objects may number fewer than 30 in our entire galaxy. Neutron star mergers forge heavy elements like gold and platinum. When two neutron stars spiral together and collide, they produce a cataclysmic event known as a kilonova. In the extreme conditions of the merger, rapid neutron capture processes forge elements heavier than iron, including gold, platinum, and uranium. These mergers are now believed to be a major source of the heaviest elements in the universe. The collision detected in 2017 confirmed that neutron star mergers produce vast quantities of heavy elements. The gold in a wedding ring may trace its origins to such a cosmic collision billions of years ago. Neutron star mergers connect the deaths of stars to the chemistry of everyday life. The violence of stellar remnants produces the precious metals of the Earth. This discovery answered a long-standing question about where the heaviest elements in the periodic table actually come from. Each merger scatters enough gold into space to form multiple Earths. White dwarfs are the cooling embers of stars. When a star like the Sun exhausts its nuclear fuel and sheds its outer layers, the remaining core is exposed as a white dwarf. These compact remnants no longer produce energy through fusion. Instead, they slowly radiate away the heat accumulated over billions of years. A white dwarf is roughly the size of Earth, but contains about as much mass as the Sun, making it incredibly dense. The material in a white dwarf is supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect. White dwarfs start out very hot, glowing white, and gradually cool and redden over cosmic timescales. Eventually, they will fade into darkness, though this process takes longer than the current age of the universe. White dwarfs are the final resting state of most stars. More than 97% of all stars in the galaxy will end their lives as white dwarfs. Our own Sun will one day join this population of cooling stellar embers. White dwarfs will eventually cool into black dwarfs. Over trillions of years, a white dwarf will radiate away all its residual heat and become a cold, dark object called a black dwarf. The cooling process is extraordinarily slow, taking far longer than the universe has existed so far. As a result, no black dwarfs have yet formed anywhere in the cosmos. The coolest white dwarfs currently observed are still warm enough to emit faint light and heat. In the far future, As the last stars die and the universe grows cold, black dwarfs will be the silent remnants of once shining suns. These objects will persist for eons, slowly approaching absolute zero. Black dwarfs represent the final, quiet fate of most stellar matter. The transformation of white dwarfs into black dwarfs will mark the ultimate end of the era of starlight. Some dead stars continue to shine for billions of years. White dwarfs cool so slowly that they can remain visible for billions of years after their formation. Their faint glow persists long after all fusion has ceased, powered only by the residual heat trapped within. This slow cooling means that white dwarfs are among the longest-lasting visible objects in the universe. By studying the temperatures and luminosities of white dwarfs, astronomers can estimate the ages of stellar populations. The oldest white dwarfs provide lower limits on the age of the galaxy itself. Their gradual fading is a cosmic clock, ticking down across eons. Even in death, stars continue to shine. The patience of white dwarfs stands in stark contrast to the brief, violent lives of the most massive stars. White dwarf cooling curves have become essential tools in stellar archaeology. The universe is not yet old enough for black dwarfs to exist. Because white dwarfs cool so slowly, not a single one has yet had time to become a true black dwarf. Current estimates suggest that the cooling process takes on the order of a quadrillion years or more. The universe is only about 14 billion years old, a mere instant on this timescale. Even the oldest, coldest white dwarfs are still warm enough to radiate faint light. Black dwarfs remain theoretical objects, predicted by physics but not yet observed. Their eventual existence is certain, but their formation lies inconceivably far in the future. The universe is still too young for its final stellar darkening. When black dwarfs finally form, the cosmos will enter an era of eternal darkness that will last for incomprehensible eons. White dwarfs are about the size of Earth but incredibly dense. Despite containing nearly as much mass as the Sun, a typical white dwarf is only about the size of our home planet. This extreme compression results in densities 1,000,000 times greater than that of water. The electrons in white dwarf matter are squeezed into such close proximity that quantum effects dominate. These effects produce a pressure that halts further gravitational collapse, keeping the white dwarf stable. The surface gravity of a white dwarf is about 100,000 times stronger than Earth's. Objects on a white dwarf's surface would be crushed flat almost instantly. White dwarfs are extraordinary examples of matter pushed to extremes. The Chandrasekhar limit sets the maximum mass a white dwarf can have before collapsing further. Stars can be torn apart by black holes. When a star wanders too close to a black hole, the intense gravitational gradient or tidal force can rip it apart. The side of the star nearest the black hole feels a much stronger pull than the far side, stretching the star into a long stream of gas. This violent destruction is known as a tidal disruption event. The debris from the destroyed star spirals inward, forming an accretion disk that glows brightly in X-rays and ultraviolet light. Tidal disruption events can briefly outshine entire galaxies as the black hole consumes stellar material. These events provide valuable insights into the properties of black holes and their feeding mechanisms. Stars that stray too close to black holes meet spectacular ends. Modern telescopes detect dozens of such stellar deaths each year, revealing how black holes grow and feed. The physics of tidal disruption has become a growing field of astrophysical research. Tidal disruption events rip stars apart in brilliant flares. The destruction of a star by a black hole produces a dramatic flare of radiation, visible across cosmic distances. As the stellar debris falls toward the black hole, friction and compression heat it to extreme temperatures. The resulting emission can be detected in X-rays, ultraviolet and optical wavelengths. These flares can last for months or even years, as the black hole gradually consumes the material. Observations of tidal disruption events have revealed the presence of supermassive black holes in distant galaxies. The light curves and spectra of these events provide clues about the masses of the black holes involved. Each disruption is a cosmic drama played out on a galactic stage. The study of these events has opened new windows into black hole behavior. Some stars survive near-death encounters with black holes. Not every close encounter with a black hole ends in complete destruction. Some stars graze the edge of the tidal radius and are stretched but not fully torn apart. These survivors can emerge from the encounter with dramatically altered shapes and orbits. Repeated passes near a black hole can gradually strip mass from a star over many orbits. In some cases, the surviving core continues to orbit the black hole, returning periodically for further close approaches. These resilient stars offer windows into the dynamics of extreme gravitational environments. Survival on the edge of oblivion is rare, but possible. Such encounters leave detectable signatures that astronomers can study. Stars can orbit close to supermassive black holes. At the centers of most galaxies, including our own Milky Way, lurk supermassive black holes, with masses millions to billions of times that of the Sun. Stars in the nuclear regions of galaxies can orbit these black holes at remarkable speeds and at close distances. In the Milky Way, the star S2 orbits the central black hole Sagittarius A*, with a period of about 16 years, reaching speeds of several percent of the speed of light at closest approach. Observations of these orbiting stars have provided some of the strongest evidence for the existence of supermassive black holes. The motions of stars near galactic centers reveal the invisible mass at the heart of galaxies. These orbits are cosmic testbeds for general relativity. The 2020 Nobel Prize in Physics was partly awarded for these observations. The fastest stars can slingshot away from black holes. Gravitational interactions near supermassive black holes can accelerate stars to extreme velocities. If a binary star system passes close to a black hole, one star can be captured, while the other is flung away at high speed. These hypervelocity stars can travel fast enough to escape their home galaxies entirely. Some have been observed racing through the Milky Way's halo at speeds exceeding 1,000 kilometers per second. The mechanism requires a close encounter with a supermassive black hole, making these stars traces of galactic center dynamics. Hypervelocity stars carry information about the environments from which they were ejected. They are cosmic cannonballs launched by black holes. Tracking these runaway stars helps astronomers understand the central regions of galaxies. Black holes can steal entire stars from galaxies. In the crowded cores of galaxies, gravitational interactions can transfer stars from one system to another. Supermassive black holes at the centers of merging galaxies can capture stars from their smaller companions. Over time, these stolen stars become part of the new, merged galaxy. Some intergalactic stars may have been ejected from galaxies entirely, and now wander the voids between galaxies. The gravitational influence of black holes extends far beyond their event horizons. They shape the distributions of stars in galactic nuclei and influence the fates of stellar populations. Black holes are not just destroyers, but also rearrangers of cosmic order. Galactic collisions scatter millions of stars into new configurations. Some stars are ejected into intergalactic space. Not all stars remain bound to their home galaxies. Gravitational interactions, particularly near supermassive black holes, can fling stars out of galaxies entirely. These intergalactic stars wander through the vast voids between galaxies, alone in the cosmic darkness. Once ejected, they are unlikely ever to encounter another stellar system. The number of intergalactic stars is difficult to estimate, but observations suggest they may be surprisingly common. Some may have originated in galaxies that were disrupted by mergers with larger systems. These lonely travelers carry with them the chemical fingerprints of their birthplaces. Intergalactic stars are reminders of the dynamic violence underlying the apparent serenity of the universe. Their journeys through the void may last for billions of years. Runaway stars race through space at incredible speeds. Runaway stars are objects that travel through space at velocities far higher than typical stellar motion. They can be created by supernova explosions in binary systems, where the surviving companion is hurled away at high speed. Alternatively, close encounters with massive black holes can accelerate stars to extreme velocities. Runaway stars are often identified by their unusual trajectories, which point back to their places of origin. Some have been traced back to specific star-forming regions or galactic nuclei. Their speeds can exceed hundreds of kilometers per second, allowing them to traverse significant distances over millions of years. Runaway stars are fleeing witnesses to violent cosmic events. The trails they leave behind can be detected as bow shocks in the interstellar medium. Some stars wander alone through the cosmic void. Between galaxies lies the intergalactic medium, a sparse expanse of gas and dark matter largely devoid of stars. Yet some stars do exist in these lonely reaches, having been ejected from their parent galaxies by gravitational encounters. These intergalactic wanderers orbit no galactic center and belong to no stellar community. They drift for billions of years through the emptiness, their light reaching no nearby worlds. The existence of such stars was once speculative, but has now been confirmed by observations. Their isolation is nearly absolute, a solitude beyond human comprehension. In the cosmic void, some stars travel forever alone. These solitary suns are among the most isolated objects in the known universe. Stars can be torn from their galaxies by gravitational encounters. When galaxies interact or merge, the gravitational forces involved can strip stars from one galaxy and transfer them to another. Tidal tails and streams of stars are common features of merging galaxy pairs. These structures can extend for hundreds of thousands of light years, tracing the gravitational distortions of the encounter. Stars in these tails may eventually fall back into one of the merging galaxies, or be scattered into intergalactic space. The Milky Way itself is in the process of absorbing stars from smaller satellite galaxies. The movements of stripped stars provide evidence of past and ongoing galactic interactions. Gravity reshapes the stellar populations of galaxies over billions of years. The Sagittarius dwarf galaxy is currently being torn apart by our own Milky Way. Some stars are ejected as runaways from exploding clusters. Dense star clusters are dynamic environments where gravitational interactions are frequent and sometimes violent. Close encounters between stars can accelerate one member to velocities high enough to escape the cluster entirely. These ejected stars become runaways, traveling through the galaxy far from their birthplace. In some cases, the dissolution of a cluster over time releases many of its members into the surrounding galaxy. The Sun itself may once have been part of a birth cluster that has since dispersed. Runaway stars from clusters contribute to the stellar populations of galactic disks and halos. Even gravitationally bound stellar groups can release wanderers into the wider cosmos. Finding the original home clusters of runaway stars is an active area of astronomical research. The light of stars can be distorted by gravitational lensing. Einstein's general theory of relativity predicts that massive objects can bend the path of light passing near them. When light from a distant star passes close to a massive foreground object, such as a galaxy or black hole, it can be bent and magnified. This effect, known as gravitational lensing, can create multiple images of the same star or stretch its light into arcs. Microlensing events occur when a compact object passes in front of a star, briefly brightening it. These lensing events have been used to detect objects that emit no light of their own, including black holes and brown dwarfs. Gravitational lensing transforms the intervening mass into a cosmic telescope. The bending of starlight reveals the hidden mass of the universe. This phenomenon has become one of the most powerful tools for studying the distribution of dark matter in the cosmos. When you look at stars, you are looking back in time. Light travels at a finite speed, about 300,000 kilometers per second. Even so, the vast distances of space mean that starlight takes years, centuries, or millennia to reach Earth. When you observe a star 100 light-years away, you see it as it was 100 years ago. The light from more distant stars can be thousands or even millions of years old. This delay turns the night sky into a kind of cosmic time machine, showing us the past states of countless suns. Some of the stars we see may have already died, their demise not yet visible to us. Looking up at the stars is literally looking backward through time. The night sky is a gallery of ancient light, each star showing us a different moment in cosmic history. Some stars flicker because of dust in their surroundings. Variations in a star's brightness can arise from dust or debris passing between the star and our line of sight. Protoplanetary disks, cometary clouds, or circumstellar dust can periodically block some of the starlight. These dimming events can last from hours to years, depending on the nature and orbit of the obscuring material. Famous examples include the star Tabby's star, whose irregular dimming sparked speculation about alien megastructures before being attributed to dust. Observations of stellar flickering reveal details about the environments of stars. The dust that dims starlight often comes from asteroids, comets, or the remnants of planet formation. Even partial eclipses by distant dust clouds leave signatures in the light we receive. By studying these brightness variations, astronomers can learn about material that would otherwise be invisible. The brightest stars can sculpt entire nebulae with radiation. Massive, luminous stars emit intense ultraviolet radiation that ionizes the surrounding gas, creating glowing regions called H2 regions. This radiation pressure and stellar wind push on nearby material, carving out cavities and shaping the structure of nebulae. The pillars of the Eagle Nebula, famously imaged by the Hubble Space Telescope, were sculpted by the radiation of nearby hot stars. The interplay between stellar radiation and interstellar gas creates some of the most visually stunning structures in the cosmos. Eventually, the radiation can erode these pillars entirely, exposing the young stars forming within. The brightest stars leave their marks on the landscape of the galaxy. Light itself becomes a sculptor of cosmic architecture. Massive stars can sculpt bubbles in the interstellar medium. The winds and radiation from massive stars sweep up surrounding gas and dust, creating vast bubbles and shells in the interstellar medium. These structures can span tens or even hundreds of light years, with thin walls of compressed gas surrounding nearly empty interiors. When groups of massive stars cluster together, their combined output can blow superbubbles that span entire regions of a galaxy. Supernova explosions contribute further energy, reinforcing and expanding these bubbles. The shell walls are often sites of triggered star formation, where compression initiates new rounds of collapse. The Milky Way's disk is riddled with these structures, remnants of past generations of massive stars. Stellar winds reshape the medium from which future stars will form. Some stars create bow shocks like boats in water. When a fast-moving star plows through the interstellar medium, it can create a bow shock, a compressed arc of gas ahead of the star. This is analogous to the bow wave that forms in front of a boat moving through water. The bow shock marks the boundary where the star's stellar wind collides with surrounding material. Some bow shocks are visible in infrared or radio observations, revealing the motion of the star through space. The shape and brightness of the bow shock depend on the star's speed and the density of the surrounding medium. Bow shocks are most commonly seen around runaway stars or stars moving through dense regions of the galaxy. These cosmic wakes trace the journeys of stars through the interstellar sea. Heavier elements like carbon and oxygen are forged in stars. The nuclear furnaces at the cores of stars fuse light elements into heavier ones. In main sequence stars like the Sun, hydrogen is fused into helium. In more advanced stages, helium becomes carbon, carbon becomes oxygen, and so on up the periodic table. Each successive fusion stage requires higher temperatures and pressures. The elements produced accumulate in layered shells within the star, or are mixed throughout its interior. When the star dies, these elements are ejected into space, enriching the interstellar medium. Life as we know it depends on elements like carbon, nitrogen, and oxygen, all of which were created inside stars. Stars are the alchemists of the cosmos. Without their nuclear transformations, the universe would consist only of the lightest elements. You are literally made of stardust. Every atom in your body heavier than hydrogen was forged inside a star that died long before the sun was born. The carbon in your cells, the calcium in your bones, the iron in your blood, all were scattered into space by supernovae and stellar winds. These atoms drifted for billions of years before being incorporated into the molecular cloud that gave birth to our solar system. Planets, including Earth, formed from this enriched material. You are a direct product of stellar nucleosynthesis, a temporary arrangement of stardust that has learned to think and wonder. The connection between human beings and the stars is not poetic metaphor, but scientific fact. You are quite literally the universe contemplating itself. This profound connection to the cosmos is one of the most beautiful insights of modern astronomy. Stars are constantly creating the elements inside you. Right now, across the Milky Way and in countless other galaxies, stars are fusing hydrogen into helium, and helium into heavier elements. Every second, billions of tons of matter are being transformed through nuclear reactions. The elements created today will eventually be scattered into space, where they may become part of future stars, planets, or even life. The process that built the atoms in your body is still ongoing. Future generations of stars will continue this work for billions of years to come. Element creation is an eternal cycle, linking past, present, and future. The cosmic forge never stops. As you rest tonight, new atoms are being born in the hearts of distant suns. Future stars will form from the remnants of today's. When massive stars die, they eject their enriched material back into the interstellar medium. This material mixes with surrounding gas and dust, becoming part of the raw material for new generations of stars. Each successive generation of stars is born from matter that has been processed through earlier stellar generations. This cycle of birth, death, and rebirth enriches the galaxy with progressively heavier elements. The Sun is a relatively late generation star, made possible by the deaths of countless predecessors. The stars that will form in the distant future will inherit the legacy of all the stars that came before. Cosmic recycling ensures that stellar evolution continues indefinitely. The deaths of today's stars are preparing the nurseries of tomorrow's. Every atom heavier than helium was once inside a star. In the first few minutes after the Big Bang, only hydrogen, helium, and trace amounts of lithium were created. Everything else, every element from carbon to uranium, was forged later inside stars. This means that the diversity of matter in the universe is a direct product of stellar evolution. Without stars, there would be no planets, no water, no chemistry of life. The elements that make up your body, the Earth, and everything you see around you passed through the heart of a star. Stars are the only natural factories capable of building the periodic table. Every heavy atom is a testament to the power and creativity of stellar fusion. The story of elements is the story of stars themselves. Some stars have names dating back thousands of years. Many of the brightest stars visible from Earth carry names that originated in ancient civilizations. Arabic, Greek, Latin, and Babylonian astronomers gave names to stars that have persisted across millennia. Stars like Betelgeuse, Sirius, Aldebaran, and Vega bear names that link modern stargazers to observers thousands of years ago. These names were often descriptive, referring to the star's position in a constellation figure or its appearance. The transmission of star names across cultures reflects the universal human fascination with the night sky. Even today, the International Astronomical Union officially recognizes many of these traditional names. The stars we see tonight carry echoes of ancient voices. When you speak the name of a star, you are using words that have been passed down for generations beyond counting. These names connect us to humanity's shared heritage of skywatching. Ancient cultures used stars to navigate oceans. Long before the invention of compasses and GPS, sailors relied on the stars to guide their voyages across open water. The Polynesian navigators of the Pacific traversed vast distances using intricate knowledge of star positions, wave patterns, and bird behavior. The North Star has served as a fixed reference point for navigators in the Northern Hemisphere for centuries. By observing the altitude of certain stars, sailors could estimate their latitude. The regularity of the stars' motions made them reliable guides for travel. Celestial navigation was an essential skill that enabled the exploration and settlement of distant lands. The stars were the first maps of the world. The knowledge of how to read the stars was passed down through generations as one of the most precious skills a sailor could possess. This ancient wisdom allowed humanity to spread across the globe. The North Star changes over time. The star currently known as the North Star Polaris lies nearly in line with Earth's rotational axis, making it appear stationary as other stars wheel around it. However, the orientation of Earth's axis slowly changes due to a wobble called precession. Over a cycle of about 26,000 years, the pole traces a circle on the celestial sphere. As a result, different stars take turns being closest to the celestial pole. Thousands of years ago, other stars like Thuban served as the pole star. In the distant future, Vega will eventually be near the pole. The North Star is not permanent but a temporary marker. The builders of the Egyptian pyramids used a different pole star than the navigators of today. This slow dance of Earth's axis ensures that every era has its own guiding star. The positions of stars slowly shift over millennia. Stars are not fixed in space. They move through the galaxy under the influence of gravity. Over thousands of years, these motions, called proper motion, cause the apparent positions of stars to shift against the background of more distant objects. The constellations familiar to us today will gradually distort and change shape over tens of thousands of years. Stars that appear close together now may drift apart, while new groupings may emerge. The speed of this change is too slow to notice in a human lifetime, but is measurable with precise instruments. The night sky is not static, but a slowly evolving tapestry. Future generations will see different constellations than we do today. The stars are all in motion, traveling on their own paths through the vastness of the galaxy. Future civilizations will see entirely new constellations. If humanity survives for tens of thousands of years, our descendants will look up at night skies that differ significantly from our own. The stars' proper motions will have reshaped the familiar patterns of constellations. Some stars will have moved across large portions of the sky, while others will have faded or brightened. New asterisms may become culturally significant to future societies. The constellations of tomorrow are being drawn today by the invisible motions of stars. Each generation inherits a slightly different sky than the one before. The night sky is a work in progress. The story of the night sky is one of constant, gradual transformation, visible only across deep time. The constellations are ephemeral patterns, captured in a single moment of cosmic history. Some constellations will disappear in the far future. The constellations we recognize are chance alignments of stars at various distances along our line of sight. As the stars move independently through the galaxy, these alignments will eventually break apart. Over hundreds of thousands of years, constellations like Orion and the Big Dipper will become unrecognizable. The patterns that have guided human imagination and navigation for millennia will dissolve into randomness. New chance alignments will form, but they will bear no resemblance to the figures of ancient mythology. The transience of constellations reminds us of the deep timescales over which the universe evolves. Even the stars rearrange themselves in the fullness of time. Our constellations are temporary features of the night sky, meaningful only to the fleeting generations who know them. The Orion we see tonight will be unknown to far future observers. The brightest star in Earth's sky is Sirius. Sirius, also known as the Dog Star, is the brightest star visible from Earth, dominating the winter skies of the Northern Hemisphere. Its brilliance is due to a combination of its intrinsic luminosity and its relative proximity, lying just about 9 light-years away. Sirius is actually a binary system, consisting of a bright main sequence star and a faint white dwarf companion. Ancient cultures around the world took note of Sirius, often associating it with gods, seasons, or important events. The heliacal rising of Sirius marked the start of the Nile flood in ancient Egypt. Today, Sirius remains a favorite target for amateur astronomers and a navigational reference. Its blue-white light has inspired wonder for thousands of years. The white dwarf companion, known as Sirius B, was one of the first white dwarfs ever discovered. The nearest star beyond the Sun is still over 4 light-years away. Proxima Centauri, a small red dwarf, holds the title of the closest star to our solar system, lying about 4.2 light-years away. Even at this relatively short cosmic distance, the journey would take tens of thousands of years with current propulsion technology. Proxima Centauri is part of a triple star system that includes the brighter pair Alpha Centauri A and B. Despite its proximity, Proxima is too faint to be seen with the naked eye. The star hosts at least one known planet, Proxima b, which orbits within the habitable zone. The vast distances between stars underscore the loneliness of our cosmic neighborhood. Even our nearest neighbor is unimaginably far away. If the Sun were the size of a grain of sand, Proxima Centauri would be another grain of sand about 4 kilometers distant. The Sun is just one of hundreds of billions of stars in the Milky Way. Our Sun, for all its importance to life on Earth, is just one star among a staggering multitude. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, depending on estimates. Each of these stars is a sun in its own right, many with their own planetary systems. The Sun is located about 2/3 of the way out from the galactic center, in one of the spiral arms. From a galactic perspective, the Sun is utterly unremarkable, a middle-aged yellow dwarf in a vast ocean of stars. The sheer number of stars in our galaxy alone hints at the probability of other worlds, and perhaps other life. The Sun is special to us, but ordinary in the cosmic census. It takes about 230 million years for the Sun to complete a single orbit around the galactic center. Most of the stars you see at night are in the Milky Way. When you look up at the night sky, nearly every point of light you see belongs to our own galaxy. The stars visible to the naked eye are all within a few thousand light-years of Earth, a small fraction of the Milky Way's diameter. The band of light we call the Milky Way is the combined glow of countless distant stars, too faint to distinguish individually. Only a handful of objects visible to the naked eye lie beyond our galaxy, including the Andromeda Galaxy and the Magellanic Clouds. The night sky is a local view of the stellar swarm in which the Sun is embedded. Looking up, we see our cosmic neighborhood rather than the wider universe. The stars above are our galactic neighbors. The Sun once had different neighboring stars. Stars in the Milky Way are not fixed in place but orbit the galactic center, taking hundreds of millions of years to complete a single circuit. Over cosmic time, the Sun's stellar neighbors have changed completely. Stars that were once nearby have drifted away, and new stars have entered the Sun's vicinity. The stars we see tonight are mostly different from those the dinosaurs could have seen. Over billions of years, the Sun has passed through many different neighborhoods of the galaxy. Our current stellar companions are temporary fixtures in a constantly shifting cosmic arrangement. The Sun's journey through the galaxy is a long and ever-changing voyage. Each galactic year brings the Sun into contact with an entirely new population of stellar neighbors. The Sun has completed about 20 orbits since it first formed. Our sky looks different from other worlds. Observers on planets orbiting other stars would see entirely different night skies than we do. The arrangement of stars depends entirely on the observer's location in the galaxy. Familiar constellations would be unrecognizable or invisible from even nearby stars. The Sun itself would appear as just another star in the skies of exoplanets, perhaps part of an alien constellation. The uniqueness of Earth's night sky is an accident of location. Every world has its own view of the cosmos, shaped by its place among the stars. The night sky is a local phenomenon, specific to each vantage point in the universe. From a distant exoplanet, our Sun might be part of a constellation that alien stargazers have given a name. Each planet in the galaxy has a unique perspective on the stellar universe. Starburst galaxies can spawn stars at furious rates. Some galaxies are experiencing episodes of exceptionally rapid star formation, producing new stars at rates tens or even hundreds of times higher than normal galaxies. These starburst galaxies are often triggered by interactions or mergers with other galaxies, which compress gas and trigger gravitational collapse. The intense star formation consumes vast quantities of gas, often depleting the galaxy's reserves within a relatively short time. Starburst regions are bright in infrared and ultraviolet light, emitted by the hot young stars and the dust around them. The rapid appearance of many massive stars leads to numerous supernovae, further enriching the surrounding medium. Starburst galaxies are hotbeds of cosmic activity and transformation. They represent galaxies caught in a frenzy of creation. These episodes of intense star formation typically last only a few 100 million years before the gas supply is exhausted. The brightest starburst galaxies can be seen across billions of light-years. Some stars are born in violent starburst galaxies. Not all stars are born in quiet, isolated molecular clouds. Many form in the intense environments of starburst galaxies, where gravitational interactions have triggered waves of star formation. The conditions in these galaxies can produce stars at extraordinary rates, sometimes giving rise to unusually massive stars. The resulting stellar populations are young and bright, dominating the light of the galaxy. These violent birthplaces expose forming stars to strong radiation fields and frequent supernovae. Despite these challenges, planets do form in starburst environments, though their habitability may be compromised. Starburst galaxies show that star formation can proceed under the most extreme conditions. The stars born in these chaotic environments carry traces of their violent origins in their chemical compositions. The diversity of stellar birthplaces adds to the variety of stellar populations in the universe. Not all stars are born equal. Some start with dozens of suns nearby. Stars born in dense clusters or starburst regions begin their lives in crowded environments, very different from the Sun's current neighborhood. Close encounters with neighboring stars can disrupt protoplanetary disks, alter orbits, and even trigger mergers. Some young stars form so close together that their disks overlap or interact. The presence of nearby massive stars bathes the region in ultraviolet radiation that can erode disks and affect planet formation. These crowded birthplaces contrast with the relatively isolated environment where the Sun formed. The birth conditions of a star can leave lasting imprints on its planetary system. Not all stellar childhoods are created equal. The diversity of stellar environments helps explain the remarkable variety of planetary systems discovered around other stars. Crowded nurseries produce planets with very different histories than isolated ones. Star clusters can sink into galactic centers and feed black holes. Over time, gravitational friction can cause massive star clusters to spiral inward toward the centers of their host galaxies. As clusters migrate inward, they may be disrupted by tidal forces, scattering their stars into the nuclear regions. Some of these stars may eventually be captured or consumed by the central supermassive black hole. This process contributes to the growth of black holes and the buildup of dense stellar populations in galactic nuclei. The inspiral of clusters is a slow process, taking millions to billions of years. Observations of nuclear star clusters and the central black holes suggest that this feeding mechanism is significant. Clusters that formed far from the center eventually contribute to its mass. This slow migration helps explain the relationship between black hole mass and galaxy properties. Even black holes can influence how stars form. The supermassive black holes at the centers of galaxies can regulate star formation across the entire galaxy. When material falls toward a black hole, it releases enormous amounts of energy that can heat surrounding gas and prevent it from collapsing into stars. This feedback mechanism can quench star formation in galactic bulges and central regions. Conversely, the jets and outflows from black holes can also compress gas at larger distances, triggering new star formation. The interplay between black hole activity and star formation is complex and varies from galaxy to galaxy. Understanding this relationship is key to explaining the evolution of galaxies over cosmic time. Black holes are not just destroyers but also regulators of cosmic creation. The connection between the largest black holes and the fates of entire galaxies is one of the most active areas of research in astrophysics. Black hole feedback may determine whether a galaxy continues to form stars or becomes quiescent. The universe may end in darkness as the last stars die. Current cosmological models suggest that the universe will continue expanding indefinitely, growing ever colder and darker. As star-forming material is exhausted, fewer and fewer new stars will be born. Existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Even the longest-lived red dwarfs will eventually exhaust their fuel over trillions of years. In this far future, the universe will contain no shining stars, only cooling remnants and the faint glow of background radiation. The era of stars, which has lasted for billions of years, is merely a brief chapter in cosmic history. Darkness will be the ultimate fate of the stellar universe. This future, though unimaginably distant, is the inescapable consequence of the laws of physics. The age of stars will eventually be remembered as a brief, bright interlude. Some theories suggest new stars could form in future universes. While the observable universe appears destined for cold darkness, some speculative theories propose that new universes could arise through quantum fluctuations or cosmic processes. In such scenarios, new stars and galaxies might form in these offspring universes, continuing the cycle of cosmic creation. These ideas remain highly theoretical and are difficult to test with current physics. If true, the end of our universe would not be the end of creation itself. The possibilities of cosmology extend beyond what we can observe. Whether new stars will light future universes is one of the deepest open questions. The fate of creation may be more complex than a single ending. These speculative possibilities remind us that our understanding of the cosmos is still incomplete. Stars can outlive the galaxies that formed them. Galaxies are not permanent structures. Over billions of years, galaxies merge, collide, and sometimes dissolve entirely. Stars ejected from their home galaxies can continue to exist long after the galaxy itself has lost its identity. Intergalactic stars drifting through the cosmic void are examples of stellar survivors. In the far future, after all galaxy mergers are complete and stellar populations have scattered, individual stars may persist in isolation. The lifespan of a galaxy is finite, but its stars can outlast it. Stars are the fundamental units of luminous matter in the universe. Their persistence is what makes the cosmos visible. Long after galactic structures have blurred into formlessness, individual stars will still be shining. Stars carry on the legacy of the galaxies that gave them birth. The night sky of the far future will be lit only by fading embers. Trillions of years from now, the last true stars will have exhausted their nuclear fuel. What remains will be a universe of cooling white dwarfs, neutron stars, and black holes. White dwarfs will slowly radiate their remaining heat, dimming over inconceivable timescales. The glow of these embers will be barely perceptible, offering only the faintest of lights. Eventually, even these remnants will cool completely, becoming cold black dwarfs invisible to any observer. The night sky of such an era will be pitch black, devoid of the familiar points of light we see today. The future holds an end to the age of starlight. Stars remind us that the universe is always changing. The stars we see tonight are not the same stars that existed billions of years ago, nor will they be the same in billions of years to come. Stellar evolution cycles through birth, life, death, and rebirth, on timescales that dwarf human history. The elements forged in stars become the building blocks of new stars and planets. Galaxies form, merge, and evolve, carrying their stellar populations through ever-changing environments. The apparent permanence of the night sky is an illusion created by our brief perspective. In truth, the cosmos is a dynamic and ever-evolving place. Stars are both the markers and the agents of this perpetual transformation. Change is the only constant in the universe, and the stars are its most eloquent witnesses. Stars in our galaxy orbit Sagittarius A, the central black hole. At the heart of the Milky Way lies a supermassive black hole, known as Sagittarius A*, with a mass of about 4 million times that of the Sun. All the stars in our galaxy, including the Sun, orbit this central concentration of mass. The Sun takes about 230 million years to complete a single orbit around the galactic center. Stars closer to the center orbit faster, some completing their circuits in just a few years. Observations of stars orbiting Sagittarius A NERT have provided some of the strongest evidence for the existence of supermassive black holes. The gravitational center of our galaxy is both a hub of stellar activity and a region of extreme physics. Every star in the Milky Way is bound to this invisible anchor. The discovery and study of Sagittarius A** earned researchers the Nobel Prize in Physics in 2020. Black holes can warp the paths of stars around them. The intense gravity of black holes bends the fabric of space-time, affecting the motion of nearby objects, including stars. Stars passing close to a black hole experience gravitational lensing, frame dragging, and other relativistic effects. These distortions can cause stars to follow unusual trajectories, sometimes tracing out spirals or precessing ellipses. Detailed observations of stellar orbits near Sagittarius A have confirmed predictions of general relativity with remarkable precision. The warping of spacetime by black holes is not merely theoretical but directly measurable through the motions of stars. Black holes leave their mark on the paths of the stars that orbit them. Gravity reshapes the geometry of stellar motion. These observations have transformed black holes from theoretical curiosities into well-studied astrophysical objects. Some stars are surrounded by mysterious shells of gas. Certain stars are enveloped by shells of gas that expand outward from the stellar surface. These shells can be produced by episodic mass loss, pulsations, or interactions with companions. The shells glow faintly as they are illuminated by the central star, creating delicate layers visible in images. In some cases, multiple concentric shells record a history of past ejection events. The mechanisms that produce these shells are not fully understood and vary between different types of stars. Observations of shell structures provide clues to the late stages of stellar evolution. These gossamer shrouds are among the most beautiful and mysterious features of stellar astronomy. Some shells have been expanding for thousands of years, carrying the history of the star's activity into the surrounding space. Stars can be shredded into streams of gas near black holes. When a star ventures too close to a black hole, it can be stretched into a long stream of gas by tidal forces. This process is so violent that the star is completely disrupted, leaving only a ribbon of material spiraling inward. Some of this gas falls toward the black hole, while the rest is flung away on unbound trajectories. The stretching and eventual consumption of a star produces bright flares detectable across the universe. Stellar streams around black holes are evidence of past destruction events. These events provide a window into the feeding habits of black holes. The death of a star can illuminate the darkness around a black hole. The rate at which black holes consume stars tells us about the density of stellar populations in galactic nuclei. Some stars are locked in long-distance orbits around black holes. Not all stars near black holes meet violent ends. Some occupy stable orbits at safe distances, circling the black hole for millions or billions of years. These stars gradually precess and shift due to the curvature of spacetime, but remain bound and undisturbed. The orbits of such stars carry information about the mass and spin of the central black hole. Observations of these long-distance orbits help astronomers characterize the properties of supermassive black holes. The stability of these orbits contrasts with the dramatic fates of stars that venture too close. Even near the most dangerous objects in the universe, some stars find safe harbors. These distant companions to black holes serve as cosmic laboratories for testing the laws of gravity. And now the quiet wonders of the stars begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the great furnaces of the universe. From the birth of stars in glowing nebulae to their long and patient lives. From the violent deaths of supergiants to the silent cooling of white dwarfs. From pulsars spinning like cosmic lighthouses to rogue stars wandering alone through the void. You have explored the hearts of suns, the forge of elements, and the strange graveyards where stars leave behind neutron stars, black holes, and planetary nebulae. You have discovered that the very atoms in your body were once scattered across the galaxy by dying stars, making you quite literally a child of the cosmos. You are part of this story. Not just an observer, but a participant woven into the fabric of the stellar universe. The iron in your blood was forged in the heart of an ancient sun. The oxygen in your lungs passed through stellar cores billions of years ago. You are stardust that has learned to wonder at the stars. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the slow pulse of a variable star. Like the patient burning of a red dwarf across trillions of years. Tonight, as you rest, the stars continue their quiet work. New suns are being born in distant nebulae. Supernovae are scattering elements across galaxies. Somewhere in the darkness, a neutron star is spinning, a white dwarf is cooling, and light that left a star 1,000,000 years ago is finally reaching someone's eyes. You are a small, warm presence within this vast glowing universe. peacefully resting among the wonders. Sleep well, sweet dreams. And may you carry with you the quiet knowledge that the same starlight that fills the night sky has always been within you. That you are made of stars, and to the stars you will one day return. Thank you for joining me on this journey through the world of stars. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the cosmos. There are more wonders waiting. More secrets hidden in distant galaxies and glowing nebulae. More mysteries to drift through on quiet evenings. Rest well. And may the gentle presence of starlight keep you company through the night. This has been Drowsy Discovery. Good night.